Hello guys, welcome back. Today I'm going to share a very interesting paper that was published only a few days ago in the archive. It is titled as ExploRLLM, Guiding Exploration in Reinforcement Learning with Large Language Models. In this paper, the authors provide a very concise design to show how to combine the large language model to accelerate the reinforcement learning in terms of sample efficiency, training speed, and stable convergence. Let's first look at the main contribution in this paper. Well, the first contribution is that the authors utilized the large language model and a vision language model to create a more compact and effective observation space. Also, they design an object-centric residue action space to simplify the learning process of the reinforcement learning agents. The second contribution in this paper is that they prompt the large language model to replace the traditional exploration strategies for reinforcement learning, such as epsilon greedy, which is very inefficient in robot settings. They combine the large language model to generate many training samples for the off-policy reinforcement learning to optimize the policies. In order to prompt the large language model to output more accurate actions for the grippers, they use a hierarchical language model policies for the large language model and demonstrate that their exploration mechanism could significantly shorten the reinforcement learning convergence time. In the experiment, the author shows that the learned ExploRLLM policy could be transferred to unseen visual appearance as well as unseen objects without any additional training. So let's first look at how they use the foundation models to tailor the observation spaces and action space for the reinforcement learning agents. Well, I want to combine the picture 2 and picture 4 to illustrate this design. So let's first look at the figure 2. They use a top-down view camera to capture the overall environment of the working space. And a vision language model is utilized here to output the bounding box for each object. And the image crops could be obtained for each object in the environment. After getting the image crops for each object, an image encoder is utilized here to output the latent features for each object. And the vision language model outputs the bounding box for each object. The bounding box can be treated as an absolute position for each object, and the object's positions are appended after the latent features for each object. After that, the robot state is also appended in the features for each object. The robot state is the position and orientation for the robot gripper. The last component is the language command, which is selected by the large language model to indicate the object to be picked and the object to be placed. After getting the features for each object in the environment, a self-attention network is utilized here to extract the features in the environment, and after that, a MLP-based policy and critic networks under the framework of reinforcement learning is utilized to output the actions. The action space is also consists of three components. The first component is the primitive action, which indicate the action to play, pick, or place. After that, the second component is the one hot object index to indicate which object to manipulate. The last component is the residue position of the gripper. As shown in figure 2, the RL agent or the large language model agents output the offset relative to the center of the object as the relative action of the gripper, and after combined with the object positions, which are the absolute positions of the objects, we can obtain the absolute actions for the grippers to execute. Okay, after illustrate how to obtain the observation space and action space based on the foundation models, let's look at the LM-based exploration in reinforcement learning, which is also the main contribution in this paper. They use the large language model-based exploration strategy in the reinforcement learning framework to collect more efficient training samples for the reinforcement learning in the beginning of the training process. The intuition is drawn from the CODES policy, which employs the large language model to hierarchically generate language model programs. The hierarchical language model programs include both the high-level policy and the low-level policy. The high-level plan output the robot action primitives as well as the objects to interact with. And the low-level task, in the low-level task, they instruct the large language model to produce a code policy to generate an affordance map according to the input image. For example, in figure 3, after prompting the large language model to output candidate Python codes to predict the affordance for each input images, there are 6 candidates output by the candidate. There are 6 candidate affordance map output by the large language model, and after evaluation the maps for each candidate, they select one candidate and decide the final pick or place positions for each objects. For example, for the letter O, they output the affordance, maybe the ring of the letter, and then they select the exact point to pick or place according to the stochastic strategy. In their implementation, we noticed that in the training phase, the ground truth in the simulation is utilized to determine the bounding box of each object, which is a good idea to quickly verify your ideas. In their experiment, they show the impact of large language model guided exploration strategies on the training space, and they also demonstrate the generalization capabilities of their trained RL policies in novel scenarios in the real experiments. So let's look at figure 6, the training curve with large language model-based exploration behaviors. For the short horizon task, we could observe that the dashed line, which is the LLM-based explore policy, could obtain a very good performance with zero shot. And if the reinforcement learning if we let the reinforcement learning agents complete the learning the task without any large language model exploration strategies, it could achieve it remains at a low level performance and also with a large variance. However, if we combine the large language model exploration strategy with the reinforcement learning agents, such as the green line, the performance of the reinforcement learning could be improved by a large margin. Let's then look at figure 6b, the long horizon task performance. The task is to put all the letters in the bowl of the corresponding color. We can also observe that the LLM-based explore policy could obtain a good performance in the long horizon tasks. However, the large language the reinforcement learning itself cannot obtain a good performance, but with 50% with 50% strategies of large language model, the reinforcement learning agents could obtain a performance that is better than the large language model based exploration policies. And in this paper, the author also provides some results for the real robot experiment. You could find more interesting findings in this paper if you read them in details. Okay, that's the overall paper reading for this paper. Now let's conclude this paper. Well, the first thing I observed is that the vision language models could provide more impact and effective observation space and residue action space for the reinforcement learning agents. And the residue action space could constrain the reinforcement learning exploration around the neighborhoods of the objects, which could guarantee a safe and robust policies for the reinforcement learning agents. The second thing I observed is that the zero-shot generalization ability of large language model is shown as a more effective exploration strategy compared with some traditional exploration policies in the reinforcement learning. So maybe you can try to use the large language model you can prompt the large language model to output some demonstrations for your robotics. And the last thing I observe is that the importance of codex policies. When facing with some specific domain, such as robot learning, it is a better choice to prompt the large language model to output the code as to output the policy instead of output some specific values. Okay, that's all. Thank you.